we are starting Mr. Card's favorite chapter, like my all-time favorite chapter in this class. I absolutely adore trigonometry. Before we get started, let's try and keep in mind a lot of stuff that you haven't really seen. It's going to pop up. Last chapter, we were in similarity, and we're solving ratios and proportions. Stuff that, you've seen it before. We're going to have stuff in this chapter that is super, super new. So this is as great a chance as ever for us to practice that growth mindset, that idea that okay, I don't get this right now, but every single day that I come in and do my best, I'm getting closer to understanding it, right? If you look at this and you go, what? Yeah, that's how you should feel. It should be very confusing right now, but we're going to get there, right? If you're thinking, I already hate this, you have this guy to thank. This is Pythagoras, okay, as in Pythagorean's theorem, my favorite theorem in all of mathematics, right? So I want to talk about the basics of trigonometry. This is where it's fun to be a math teacher and also, show you guys where this stuff comes from. Okay, so trigonometry, let's literally break down the word. The Greek for triangle and the Greek for measure. So we are literally doing a chapter that is all about the measurements within triangles and the ratios and the relationships that they have to each other. This stuff dates all the way back to the 3rd century BC. So in my research on this, it looks like the Greeks were pretty big on calculating chords. And in India, that's where we have found the earliest known tables of values for the trigonometric ratios. So sine, cosine, which we'll get into later, right? But always fun to see, right? It wasn't just the Greeks, right? There were, there are plenty of people up to some pretty cool math stuff back in the day. Okay, so we are starting with basics, and one of the essential basics, right, is the Pythagorean theorem. And typically, when I say, does anyone have any prior knowledge, people would go, yeah, I know exactly what it is. We've kind of already you've mentioned it before, Mr. Card. Like, we've kind of used it at least once or twice. Well, now we're officially really going over it. In a right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the legs. So basically, again and again, Pythagoras keeps noticing, okay, you're telling me that if I take the leg and I square it, I take the other leg and I square it, and I add them together, it's the exact same as if I just squared this hypotenuse. Fascinating. And so he makes a theorem out of it. I will actually prove this to you when we get to the end, when I talk about how it's related to distance formula. Right? We learned distance formula way back in chapter 1, and I promised you, hey, later in the year, this is going to pay off. All right. If we were in school, and if being in school wasn't potentially, if this activity wasn't potentially a super spreader event, we get into big groups and I give you guys a bunch of starburst. Typically, I need to bring a bunch because the activity fails if you wind up eating them. But I ask you to make a square on the sides of a triangle, and basically we create this visual proof of the Pythagorean theorem. That if this length CB is 5, then you need to go 5 down, 5 over, 5 up. And you do that with starburst. And then I say, hey, what happens if you take this box and this box, these two squares, if you put them together to make one square, you'd find, I can actually make it the exact same size as this one. So it's a great visual proof. Now we get to talk about what problems are going to look like. Okay. So in a situation like this, I'm expecting you to be able to say, that's the hypotenuse. I know because it's across from the right angle. So 8 squared plus 6 squared equals x squared. 8 squared is 64. 6 squared is 36, and this is my favorite type of right triangle. It's a 3, 4, 5. We'll talk about those Pythagorean triples later on, and that sentence I just said will make way more sense. But when I add these together, I get 100, and I go, oh, thank God. Whew, it's a perfect square. Oh, I love it when that works out, right? When I wind up taking the square root of both sides here, I'll get x equals 10. Not negative 10, even though Some of you smarty pants out there are going, oh, what about -10? Yes, but do we ever measure distance negatively? No. So you're technically right that the answer to what's the square root of 100 is 10, but also -10, but we don't measure distance negatively, so we're kind of just going to ignore that. So that was a nice easy one where it was a perfect square, but uh-oh, that's not always going to happen. All right, when we're working with radicals, what do we need to remember? Rules like this, right? Being able to simplify stuff because it's not always going to work out. What's the goal? I really like this picture. Okay, because see how it like color codes the 36, the 16, the 25, because it's really getting you to focus on the idea that when you split these things up, you need to do so that one of them is a perfect square, because that's the only way that it actually simplifies into something nice. 48 is divisible by other numbers besides 16. Why don't I just split it into 24 times 2? Well, because neither one of those is a perfect square, right? Why don't I do 9 times 8 for 72? I guess, we could do that. It would lead to more simplification. I'm realizing as I say it out loud, right? Right. You'd have 3 root 8, and then 8 goes into 4, root 4 times root 2. So you still get 6 root 2. So maybe that's a bad example. But the point I'm trying to make is I like that we're really focusing here on what is the goal. The goal is not just to split it up into its factors, but where one of those factors is that perfect square. That's so important. So we got to remember that stuff. Rationalizing will probably pop up as our questions get more complicated, right? Which the way you're not really supposed to have a radical in your denominator. So how do you get rid of it? Well, we know that the opposite of squaring something, the opposite of square rooting something is squaring something. They're called inverse operations. So that's what I'm doing here. When I multiply these, what I'm saying is root b times root b. That's root b squared. And so I just wind up with just b. And then you obviously just have to worry about the numerator. And you don't really care how the numerator works out. As long as this works out so there's no radical, you're safe. Here's a great example to pause and look at. It's a good problem, good challenge problem. Find the area of a triangle that's 1/2 base times height. This is a good problem for introducing the idea that, guys, when you're dealing with isosceles triangles, right? So I have 10, 13, 13. When you create this altitude, all I need to do, right, is I need to be able to do 1/2 base times height, right? All I want to be able to do is area equals 1/2 times the base times that height. How do I find the height? Using the Pythagorean theorem. Because you want to be able to say, oh, if this individual side is 5, then I can set up a Pythagorean relationship to solve for that height. Right? Isosceles triangles always split into 2 right triangles. Pretty helpful to think about. Right? So we can see the solution here. That's another Pythagorean triple, by the way. 5, 12, 13. A pattern that occurs again and again. So that's enough for one day. We're going to do some practice Pythagorean theorem work to finish out our lesson. You guys should be very excited about this chapter, though. All right.